dispatches all the different instructions, just emulate all these instructions, instruction by instruction. For kernel mode code, we could do that. We can run user mode natively because there's no problem with user mode. It still runs in user mode, behaves perfectly, and behaves the same. And we could just emulate kernel mode code. But this is just not optimal. We could do recompilation. Recompilation is a faster way of interpretation, and there are so many products out there that do recompilation, and all of them do recompilation from one CPU architecture to another CPU architecture. They just take binary code from, for example, 86K code from the Amiga emulator and convert it to x86 code, or PowerPC to x86 for PowerPC. And also the Xbox 360 has an emulator that converts old Xbox games to the new PowerPC processor shipping in the 360. So what VMware does is exactly the same approach, but it changes x86 code to safe x86 code. So it takes x86 kernel mode code and replaces, well, it can take most instructions verbatim. It doesn't have to do big translation of register sets and all that. It only has to see what instructions might be problematic and replace them with some other instructions or explicit calls into the hypervisor. So on this slide you can see on the left side what the original code would look like, and on the right side how it could be replaced. For example, some LGDT could be replaced by just calling some routine. This would be now be some user mode routine. We could also syscall into a hypervisor. That's a matter of implementation. And that's the same with the other ones. And those that don't have to be translated just can sit there verbatim. And while we're doing this anyway, we can emulate some things. And these are some, well, there is a performance impact by doing all this. If we had a not so broken architecture, then VMware could be a lot faster. But VMware is quite fast because it does do extra optimizations because they have all this infrastructure in place already. So normally if there's a syscall, I showed you that you have to go into VMon, it traps, it goes into VMon, it goes into VMware, it goes down to VMon again, and goes into kernel mode, into the kernel code of your guest code. But this can be optimized into this by staying in user mode, by staying in the guest code, by just replacing the syscall code with some other code that just does a small call, that just changes some registers or something, and then swaps into the kernel mode code without any world switches, without any context switches. If you think this is not safe because it changes the state of the emulated CPU or something, then keep in mind that all this changed code there is code that gets written by VMware, and user mode code or kernel mode code has no way to read this changed code back in and do any funny things with it. So there's some extra protection in place so that there's no way for user mode or kernel mode code inside the virtualization to find out that the code has actually been rewritten. Yeah, but the problem is this is quite complex. So VMware can do it, Parallels can do it, Virtual PC can do it, QEMU can do it to some extent, not so fast. But if you just want to have some small virtualization, for example, for PowerPC, there's the great Mac on Linux project, or also the Mac on Mac port, which isn't so complex, which is a product which has been existing for quite some time, and it works, and there's, well, except for QEMU, which is quite good now, there hasn't been an alternative for x86, because x86 was just too complex for all this. You cannot have lightweight VMMs for, there are many good ideas why you would want to have some VMM in some application. That is why both Intel and AMD introduced extra technologies with their newer CPU generations. I think most CPUs sold since this year include either VT or SVM technology. Well, it would be nice if there was just one technology, and it would be nice if it only had one name, but VT was called Vanderpool, and is now called VT. SVM was called Pacifica, and is now called SVM. So whenever you hear any of these, it's basically the same technology, but it is totally incompatible, of course. VMware, for example, can do both, and they have a very thin layer of abstraction between the two. It's just different opcodes. It's a bit different, but the system is the same. And the system, how it works, looks like this. It is a three modes approach. You have a user mode, a supervisor mode, and a hypervisor mode. So you don't have to fake anything. They could have changed, or they could have fixed the broken architecture just by making some instructions trap, which didn't trap in the first place. But this way, the hypervisor can still get a little easier. You can have some performance or some simplifications in your software with having that third mode. They call the hypervisor mode root mode, so the CPU will, typically if you boot up a system, the CPU will run in root mode, and if you don't use virtualization on, for example, the new Core CPUs, you'll run in root mode, and if you turn it on, the virtual machine will always run in non-root mode. And non-root mode will then have a supervisor mode and a user mode. So let's look at how VT, or also SVM, I'll stick with the example of VT, how it works in practice. Before VT, for example, world switches, well, the main point is that you can just very easily do world switches, either automatically or if you want to have an explicit world switch. Before we had VT, we had to use some code like this. We had to save all the registers, even the special registers, and we had to load a new register set from RAM, everything manually. Switching back, no, first this. Now VT only has one instruction for this. If you do VM enter, you have one pointer that is already set up in a new special register. You do VM enter, and on this pointer you have your complete register set, all the internal state. You don't have to care about the internal state, it's all managed by the CPU. You do a VM enter, and it replaces, it saves your state and loads the new state. And it's then in guest mode. Runs the guest kernel until some interrupt or something occurs. Before VT, switching back to the host would mean you had to redirect all your interrupt vectors and have some small code mapped into the guest that could intercept all the interrupts and do the world switch back. And have some code like this again, saving all the registers and loading the old register set. With VT, everything you have to do is subscribe to interrupts. You have to tell VT what interrupts and what exceptions you want to have. Typically you want to have just all of them, that you can do good virtualization, or if you want to do very lightweight virtualization, like Blue Pill or rootkits or these things, you don't want to have any interrupts. You let the system do everything, then it cannot be measured that you're running at all. Well, for most of the time, that is. You can just run the whole thing, and only if there is something special going on, like a keyboard interrupt or something, you can only intercept that single interrupt. So it gets a lot easier. Now what about speed? Does VT or SVM, does it really make everything faster? The point is that VT and SVM make development easier. For example, now we have Zen. Zen already supports both these technologies. Without VT or SVM, it cannot do it. There's so much extra complexity that would have coded into Zen, and nobody had done that. But it's not necessarily slower. It's not necessarily faster. That's the point. VT is not necessarily faster, and in some times it is slower. For example, VMware claims that their solution is faster than if they were using VT. For example, if you have the current version of VMware, any version of VMware, even on a VT-capable CPU, it will not use VT unless it really has to. For example, in 64-bit, there's some bug in AMD CPUs and also Intel. Well, AMD has fixed this bug, but Intel has not. So VMware has to use VT to work around this bug. So they use VT, but otherwise they don't, because they say without VT it's faster. Because the key in being fast is avoiding traps. As I showed you on that one slide, if you want to switch between user mode and kernel mode inside the guest, you have to do so many world switches if there is a trap. But if you do recompilation anyway, you can avoid all these world switches by just putting code in place that does the same thing. And all the solutions out there do this already, VMware, just like Parallels and all that. So VT isn't such a big deal. If you want to have fast virtualization on your system, you shouldn't really care about VT. If you want to code yourself some things that deal with virtualization, then VT is a great thing. Okay, that was my conclusion about VT and SVN and about virtualization in general. So if there are any more questions, I'm open for them now.
Okay. If VMware uses all this recompilation stuff, why does it still need a kernel module?
The kernel module is always needed to do world switches. For example, you want to change the memory layout. For example, if you're in the state that the VMware user mode application is running, then it has its specific memory layout. Then you want to switch into some Windows application, and this Windows application needs its specific memory layout. In a user mode application, you cannot shuffle the pages around as you want. You basically have to do a CL3 switch on Intel. You want to reload your page table. You want to completely change your memory layout. For this, you need kernel mode code. You cannot do this in user mode.
What you're saying is that QEMU works because it does more recompilation stuff, or what? Because QEMU doesn't need a kernel module?
That depends. I'm not so familiar with QEMU, but I think it has two different modes of emulation. If you don't have a kernel module, then it cannot shuffle around the address space totally, so it has to emulate this and is therefore slower. But QEMU has a mode with the QEMU kernel module which can speed all this up.
Okay, so it's just more recompilation and stuff.
If you don't have a kernel module, the recompiler will just do more and be slower.
Using VMware with recompilation will need more memory. And if you have applications that have a lot of code, then it can be noticeably much more memory what you need with VMware.
Yeah. Was that a question?
Yes.
Yeah, that's true. You have basically all the user mode code can be just executed verbatim, but all the kernel mode code has to be translated. So if you have like 5 megabyte kernel or something in a system, also some data structures are duplicated. And also this is wired memory. You cannot just swap this memory out. This is expensive memory. Yeah. So without recompilation, you wouldn't need that.
So I've seen a couple pieces of malware that will jump to the middle of an instruction so that they get a different interpretation of that instruction because you're starting from a different byte. My question is, if VMware is doing translation from x86 to safe x86, do you think there's any potential for causing VMware to pass instructions to the processor that it thinks are safe but are in fact, because of some kind of contextual shift, unsafe?
I don't think I understand the question.
The question is basically...
Who understands the question? Oh.
Do you think there's any way we can make VMware execute unsafe instructions from the guest OS and the parent OS?
If VMware isn't perfectly safe, that is possible. It's a lot of code, and it's very complex, and there may be ways to pass some instructions that VMware doesn't cope perfectly with. I think there have been exploits in the past, or there have been detections or something.
Cool, thanks.